the chat and thank you. I will put the Q&A in the chat. Please put your questions in there, and we will read them out in the last 4 minutes or so of talk, and get those answered. And if your question doesn't get answered, put them in the chat anyways, and Akash might be able to get to them after the talk is over. All right, take it away, Akash. I will drop the link in just a moment.
Wonderful. Thank you so much, Karina, and thank you all for attending today. My name is Akash. I'm the CEO and co-founder of Working Trees, and I'm really excited to chat with you today about how we can leverage digital sensing technologies for climate adaptation. And we're going to talk about sensors on smartphones, on drones, on planes, on satellites. But first, we need to talk about trees. So let's talk about trees. Trees and forests actually absorb about 1/3 of annual human-driven carbon emissions right now. So they're already this really potent and important climate sink and GHG sink. Growing new trees could also provide about 30% of the mitigation required to keep warming under 1.5 degrees Celsius and avoid the most detrimental impacts of climate change. And actually, planting trees in deforested landscapes and on agricultural lands, practices called reforestation and agroforestry, represent an opportunity of over a gigaton a year of CO2 equivalent. So this massive lever against climate change that we can deploy at scale. And trees fix so much more than just carbon, right? So trees planted in agricultural landscapes improve the water retention capacity of the soil. They filter out pesticides and fertilizers before they reach waterways or streams and rivers. So they improve water both quantity and quality. They also provide habitat for biodiversity and ecosystems. And increasingly important, they provide shade and cooling for people and livestock. And this is critical in a world that is getting warmer and warmer, and where we're experiencing some of the adverse effects that correspond to heat stress, both in urban and rural areas, and both for people and livestock. Trees can also provide climate resilience. They break wind, they limit the impacts of extreme weather, they reduce erosion, and they have so many other benefits. And some of those benefits also are around production and livelihood. So they produce fruit and nuts, they can produce fodder for livestock, and so they can be an economic lever for people to improve their livelihoods as well. Additionally, there are over 1 billion hectares globally that can be restored with tree planting projects. So the yellow areas on this map are showing the most potent areas, and this represents a land area about the size of the United States, so totally massive. And if restored at scale, it could actually help reduce about 2/3 of the cumulative anthropogenic greenhouse gas emissions since the 1800s. So again, an absolutely massive opportunity here. But it's not all good news. I am sad to tell you that right now, the scale of reforestation and agroforestry activities, and as a reminder, that's planting trees in deforested landscapes and on agricultural lands, these activities are still really small compared to deforestation and the magnitude of deforestation. So this pie chart is kind of showing the magnitude of stable forest in green, forest loss, so deforestation in purple, and then forest gain in blue. And you'll see that the current rates of forest loss are actually double the amount of forest gain. So the question arises, why is this happening, right? And it really comes down to monetary incentives. And so right now, there are more monetary incentives to deforest our land as opposed to the monetary incentives corresponding to reforesting the land and growing trees. And so there are actually cost incentives in place for growing trees right now. Think about the governments and the corporations with net zero climate goals who will actually pay land stewards to plant and manage trees and sequester carbon on behalf of these organizations with ambitious net zero goals. But unfortunately, this isn't really happening at a large scale. And one of the key reasons why is the cost of monitoring, right? These organizations need to be assured that their investments are being used appropriately, and they need visibility and high quality monitoring into the carbon sequestration and GHG sequestration resulting from their efforts. So how do we do some of this monitoring, and how can we do it in a cost-effective and scientifically rigorous manner? Well, there are a lot of ways that we can measure the amount of biomass stored in trees. We can use instruments deployed on the ground, on unmanned aerial vehicles, on planes, and on satellites. And you might use a different tool depending on the area of interest that you're studying. And there are trade-offs associated with all of these instruments, right? Ground-based and airplane-based sensing methods actually are very expensive. And satellite methods, on the other hand, are free. However, you still need the ground-based data collected by foresters and other researchers to calibrate and validate those satellite-based models to make sure they're doing a reasonable job of actually estimating accurately the biomass stored in trees. So, right, there's essentially this trade-off between accuracy and scalability, right? At the satellite scale, you have this really high scalability. These satellites are orbiting the Earth all the time, collecting data. They are providing free data in a lot of cases, since it's taxpayer money being used to build and deploy them. But if you need to understand what's going on at the individual tree or farm level, satellite data is just not going to cut it most of the time. So, these satellites are amazing tools for large areas. You can make maps like this describing tree cover and biomass, but they're really missing something at the small scale. At the higher accuracy end, at the other end of the spectrum, you have tools like tape measures, right? Like, we don't actually need any sort of fancy technology to estimate the amount of carbon stored in a tree. The traditional way of doing it is you actually just measure the diameter of the tree, and then you use an equation specific to that tree, which you can plug in the diameter to, and you can get an estimate of the amount of carbon stored in that tree. But this scales really poorly, right? Like, we can't go out and measure all the trees in the world and then come up with the total amount of carbon. But at the same time, we need this ground-based data to calibrate and validate our satellite-based models and our estimates of biomass and carbon derived from those middle two sensing platforms from drones and airplanes, right? So how do we actually go out and measure biomass right now? So it actually is what this gentleman in this photo is doing. You go out to trees, you stick tape measures around them, and you record the measurements in your notebook or your clipboard. You take them back to the office, input it into a spreadsheet, and then you can use an equation to estimate the mass of carbon in that tree, right? But this is really costly if you think about it in terms of both time and labor. You need to send out these crews of people. They can travel great distances. They're recording these manual measurements and then writing down the data over time. And then they have to go back to the office and plug them into a spreadsheet. And there can be room for transcription errors. And this process is just inefficient, right? So this guy's thinking, probably as he's doing this, like, surely there's got to be a better way. And actually, that's what I was thinking about when I started working trees. And for a little bit of context, I was a PhD student in geophysics, and I was actually working on using satellites to study groundwater changes in California's aquifers, which is probably a talk for a different day. But I found myself asking the question, like, what if we can give a non-expert the tools that they need to reliably estimate carbon in trees? And what if we could do it like using the tools that were already in their pockets, right? So smartphones. So this is how Working Trees got started. And being that I was interested in this kind of thing, I thought, okay, maybe I can leverage my background to help build this kind of technology on mobile phones that we can use to accurately measure tree biomass. So that's just what we did. And here I'm showing a video of the app, of our phone app in action. Right now I'm measuring the diameter of a tree, taking a photo of all the measurements. The app uses augmented reality technology to model surfaces and measure distances. Right now I'm measuring the height of this tree, and we can also record lots of metadata about the tree automatically, things like the location in latitude and longitude coordinates, things like the time which the measurements were taken, things like the angle and bearing of the cameras when they're taking the measurements. Here you're going to see some of that metadata. There's a map where the tree was measured, and there's the diameter and the height and the corresponding photos. And if you want to play around for yourself, you can go to this URL, or you can scan this QR code and download the app and let us know what you think. So we also have more functionality in the app that can help somebody kind of manage their sampling plots and their sampling routines. So you can organize the areas that you're sampling trees. You can actually record the locations on a map interface that's just as easy as dropping a pin when you're doing planting projects that you might want to monitor in the future, but record the locations now. And then, of course, the measuring trees functionality, you can select species, record measurements of diameter and height, record locations, view the metadata, view the location and latitude and longitude coordinates, and so on. And let's talk a little bit about some of that metadata. We record the GPS coordinates and the uncertainty, as I said. We record images of the trees and the measurements, including the azimuth and the orientation of the phone when they were taken. We record timestamps and the make and model of the phone. And critically, we can collect all of this data without actual network access. So even if you don't have phone service, we store the data locally on the phone, and then when you get back into service, the data gets uploaded to our cloud database. So you can go and measure out in these remote areas without service. Now, importantly, we needed to test this technology rigorously to make sure it was accurate. And so that's just what we did in partnership with Virginia Tech University, which I affectionately think of as the Cal Poly of Virginia. And so we went out with a team of 4 people to 2 farms in near Blacksburg, and we measured about 150 trees using the phone app and then using tape measures. And I should note that the trees were measured double blind, so the people who used tape measures had no idea the measurements that were being collected by the app, and vice versa. The people using the app had no idea what was being collected via tape measures. And so here I'm just showing some of the results. The x-axis in this plot is showing the manual diameters measured using tape measures. And the y-axis on this plot is showing the app-based measurements of diameter. And what you see is a really strong correlation between the manual measurements and the app-based measurements. We have a correlation of about 0.95 in terms of the r-squared value. And the results also suggest that we can measure these diameters accurately to within 1 inch, right? Our mean absolute error is about 1.9 centimeters, and this corresponds to about 8.3%. On this plot, each color is showing a different species of tree, and the line of best fit, the regression line, is shown in red. And you'll notice that the app is slightly conservative, so it underpredicts diameter across most species and across all of these data, but we're actually okay with that because we want to be conservative in our estimates. And importantly, the app took about 1/2 of the time compared to the manual approach, and that actually doesn't include the time that it takes to transcribe the data collected back in the lab. We also analyzed the uncertainty at the species level, so we were able to measure trees comprising 4 different species, and the results are shown in this table here on the left, and on the right I'm showing histograms and distributions of the app-based measurements shown in black and gray, and then the manual tape measure base estimates shown in blue and orange for black walnut and honey locust. And the big takeaway here is that we're doing pretty well. We're matching the distributions well, and we have less than 1 inch of error for all of our species. We also were interested in determining how different users might have uncertainty when they use the app to measure diameter. So what we did was we analyzed the uncertainty for each tree measured by different users. And that's what this plot is showing. It's the same scatter plot as I was showing before, except the y-axis error bars here are showing the uncertainty associated with multiple users of the app. So you can see there's still some spread. There's a little more spread, but we're doing pretty well. We still have that really tight correlation, r-square value of about 0.95, still measuring accurately to within 1 inch. And the violin plots on the right-hand side are showing the mean diameter for one species on the left, and users of the app are shown in blue, orange, and green, while the manual measurements are shown in red and purple. And the takeaway here is whether you use manual methods like the tape measure or you use the app, you end up with a pretty similar mean across all of the species that we investigated. We're also working on tree counting algorithms that we can use to extrapolate data collected from the app across larger distances. This is ongoing work, so I'm not going to talk too much about it, but suffice it to say that we can use some very simple computational techniques called difference of Gaussians and Laplacians and use satellite or aerial data to then count pretty accurately the number of trees in an area. And we're also developing tools to improve the transparency and communication aspect of our work. So this is a screenshot of an online dashboard that we're developing where a user can use our app, go out and measure a bunch of trees, and then log on to this app on the computer, and they can view aggregate statistics like how many trees did I measure, what is the total carbon stored across this area, what is the mortality rate, like how well are these trees surviving, what different species are there, and so much more. You can also view the photos that were collected and other metadata that I mentioned before. So what's next? What are we excited about working on in the future? So we actually think that there's maturing technologies in 3D modeling using phones and drones, which lets you make photorealistic models like the one that you're seeing on the right. And for the cases of weird or irregular trees that have multiple trunks, like this one, these models can actually do a great job of recovering the correct biomass and be a better way to do this than using the equations that I described before. But we also have to understand the uncertainties and the trade-offs, and that's something we're working on now. So that's really all I have. I hope you enjoyed this. If you're interested in these kinds of things, please feel free to get in touch. My email is on the screen. You can check out our website on the screen. And if you want all the gory details about the study that we did, you can check out our recent paper in Forests, also on the screen. You can download our app using the QR code on the top left. And I want to just give a quick shout out to all of our partners listed below before I stop and take questions. And with that, thanks for your attention.
All right. Thank you everyone for attending. I see one question in the chat. I believe you covered part of this question, but the question is from Margot Cap. It says, what is the level of accuracy of working trees?
Yeah, so we're over 90% accurate. I think it's 91% exactly. And that's across a sample of over 400 measurements that we compared to tape measures. And we sort of broke down the accuracy statistics in a number of different dimensions, and you can view more about it in the paper. But the short answer is we're over 90% accurate compared to tape measures when measuring diameter.
I just saw another question in the chat from Cassandra Huezo. Is there a greater error in larger/taller trees? There's a couple of these. Maybe take them one at a time.
Yeah, I see them there. Great questions, Cassandra. I will address them individually. So when we're measuring height, since we use a surface detection algorithm, it is tough to measure taller trees, especially those that are really like spindly and narrow at the top, because the AR algorithm struggles to identify those surfaces. So we're actually investigating some more like trigonometry-based approaches to come out with, to reduce that error and uncertainty. And we have some follow-on work going on to investigate this. Cassandra's second question was, do you have to use fixed radius plots? The answer to that kind of depends on what sort of sampling protocol you're following. So we do like a census-based approach, which means we do measurements at the tree level and then extrapolate based on the number of trees. But if you were doing sort of an area-based sampling approach, like is more traditional in forestry, then you would use a fixed radius plot. And we do actually have a sampling routine that can accommodate a fixed radius plot. And Cassandra's third question, also another good one. Do you take multiple angles to account for trees that are not perfectly cylindrical? Great question. Not something we're doing right now, but I do think this is something that could be addressed with a sort of more 3D modeling type approach. where you can actually recover the diameters and the variations in diameters from a number of different angles. And lastly, her question on, does this technology meet the strict standard for carbon markets? We're currently in review with one of the carbon market registries who's evaluating the technology for broad use, but we certainly designed it to be broadly applicable, and we hope that others in this context can make use of it. And we are sort of using it in the carbon restoration projects that we're running. So I think that was all of them, but happy to take more or chat with you later, Cassandra, because those were really great questions.
All right, and there's, if you have time, there's one more question from Andrew Fricker in the chat in Zoom.
Yeah, how many active users are using the Working Trees app? You know, Andrew, I wish I knew. I think we have like 4 reviews in the App Store, and we have a number of customers who are using the app. I don't have specific numbers about like the number of staff at those customers and those organizations that are using, but I would estimate probably a few dozen at this point. Yeah, I'll leave it at that.
I see a question in the Hova chat. Will there be a recording of this presentation? Yes, there will be. It should be available to you afterwards. There are more questions in the Hova chat. Akash, are you able to get to those after the talk, or do you want to answer a couple of them now?
I'm happy to answer some now, but I can't see those questions. So if you wouldn't mind reading them, I could definitely answer
I will
them.
definitely read them out. Who is the target user audience for Working Trees? Also, do they receive any incentives for using it? This is from Isabella Nava.
Yeah, so we sort of have 2 audiences. So we work directly with farmers and ranchers who are interested in planting trees on their properties and measuring the carbon and receiving incentive payments for the carbon that they're storing. But we also work with organizations who are interested in doing restoration or monitoring trees that they've planted. So we work with dairy companies and we work with NGOs who are doing this type of work, but really just want access to the monitoring technology to speed up their operations and accounting processes. So those kind of 2 different sets of actors.
And another question, would making a 3D scan of the tree be significantly more accurate than the current methods using LiDAR feature on phones?
Yeah, great question. So my opinion is that it would be significantly more accurate, and I'll tell you why. So the way that we measure tree biomass right now is, as I said, you just measure the diameter and or the height, and then depending on the species, we have an equation that you can plug those parameters into, and you can get an estimate of biomass. Now, these equations were developed by the Forest Service about 50 years ago, and they may be regionally specific. They may include only forest trees and not be a great fit for trees in urban or agricultural settings. And they have uncertainties that really aren't accounted for. So if you could have a sort of 3D morphometric representation of the tree, you can look up density values in a wood density database, and then you have a volume, you have a density, and that's all you need to go to a mass. So instead of using these kind of like decades old equations, which are still very valuable and are the way that we're doing things right now, you can kind of move towards this more tree specific characterization that is able to capture and accommodate some of these unique morphological characteristics at the tree level, rather than being based on these correlations that were done at the species level about 50 years ago. I also will mention that I'm based here in SLO. I wanted to mention that earlier. So if anybody wants to chat about this, we can meet up in person. And in fact, some of the screenshots and things you saw before are trees like in SLO and in my backyard and things like that. So not a question, but a comment, and happy to take more questions too.
Yeah, there's definitely more questions that are here right now. Can the app and methods be used in the global south to help communities monitor forest stocks or potential payments for ecosystem services in the tropics?
Yeah, we definitely hope so. there are many considerations with working with these communities, such as like lack of access to network and lack of access to like newer model phones. So we're working on an Android version of this app right now that can be like backwards compatible enough so it doesn't have to use a new LiDAR phone. It can just use the camera system on an old Android phone. We still need more testing to do. The sort of augmented reality and 3D photogrammetry libraries on iOS and Android are slightly different. So we'll need to do more testing and validation and research to confirm the accuracy. But we definitely think and want users all around the world. And we want to be able, we want to get these people access to incentives for the important land steward work that they're doing.
Awesome. I see one more question from another one from Isabella Nava. How can the biomass be utilized for climate adaptation?
Yeah, so the idea here is by doing better and more transparent accounting of the biomass, we can give more assurances to the organizations looking to purchase carbon offsets or reduce their emissions footprints through paying other people to sequester biomass on their behalf. And if you've heard about kind of carbon offsets, you've probably heard about all the scandals and all of the fake data and the bad projects. And like, that is exactly the type of thing that we are trying to fix. We're trying to be really transparent, totally scientifically driven, and build these systems in a way that people who are interested in investing into restoration projects can be really confident about the outcomes that they're achieving. So again, trying to use technology as a lever to not only achieve climate action in terms of planting trees and experiencing the carbon benefits, but directing funds from these organizations to the land stewards who are really spearheading these activities.
All right. Thank you. I believe we got to all of the questions in HOVA. Apologies if I did not. I will reload one more time to see, since there's not currently a chat coming in. So whoever sticks around is sticking around, and that's okay. I wanted to redirect everyone to just the HOVA site for the next talks that will be happening after this. They won't be in the same Zoom, so you'll have to go back there and enter a new one. Yes, okay. We did cover all the questions in HOVA. So thank you everyone for attending. Thank you, Akash, for presenting. This was very interesting. And I hope you guys join some other talks that are coming.
Thanks so much. And please get in touch if you're interested, and enjoy the rest of the talks. Take care, everybody.